Our challenge was to create a robot that was capable of scoring 1 goal per minute with an orange golf ball in a 2x2 meter field whilst navigating around obstacles. It had to not exceed a maximum diameter of 180 millimeters and a maximum height of 255 millimeters. With these constraints in mind, Steve was born. What is Steve? Well, Steve stands for not really much, really. Just Steve. We named him Steve Robeckham because he plays football like the lad he is. He does a bunch of things, kicks goals, moves uniquely across the field, avoids obstacles when he feels like it, and uses his camera to see what's in front of him. All in all, he's a top player, but his creation wasn't so simple.
Steve has 4 main systems that integrate with each other to make him into the player he is. There's the motor drive subsystem, which was developed by Anka, the kicker dribbler system, which was developed by Josh, the vision system, which was developed by Nick, and the navigation and AI system, which was developed by Nasan. Steve didn't make it easy for us, but we were able to whip him into shape in time for the football season.
Robeckham has an omnidirectional drive system which contains 3 3D printed omnidirectional wheels with motors at the angles of 60, 180 and 300 degrees from the front of the robot. This drive system makes the robot more stable due to 3 wide friction points and gives a higher degree of freedom to move while rotating around its axis. Initially, the camera sends an input to the Raspberry Pi, and then the controller decides on the direction based on Steve's surroundings. Some specific mathematical formulas are used to calculate the speed and direction of each wheel. These speed vectors are sent to the motor drivers, which turns the motors to achieve desired movement.
For the kicker, Steve utilizes what's called a crossword kicking system. Taking inspiration from traditional crossword designs, it uses a rack and pinion with a rubber band connected to the rack to provide elastic potential energy when pulled back. To automate the entire system, a DC motor is connected to the pinion, which pulls back the rack until it reaches the loaded point. Normally there would be a latch which holds the rack in place before releasing. However, to simplify this process, the pinion teeth were cut until the number of teeth is equal to the total distance needed for the rack to travel before reaching full load. To prevent the rack from sliding forward due to the gathered potential energy of the elastic band, the selected DC motor connected to the pinion had to have a high gear ratio. As such, a 1000-to-1 gear ratio motor was sufficient enough to keep the rack loaded at full load. As for the dribbler, the design of the dribbler was 3D printed out and the size of it was mirrored to almost perfectly fit the golf ball and hold it. Rubber bands and balloon material were added to the dribbler to provide extra grip when trying to add backspin onto the golf ball.
Upon Steve's initial startup, the camera loop is initiated. By using the ball as an example, this loop goes through the following steps. First, a color mask is applied to the video, where the orange color of the ball is separated from the rest of the image. Then, for only the largest area of orange-colored pixels, a box contour is drawn which encompasses the color block. From there, a quick calculation can be made for the ball's center point within the viewing range and another for its distance. This process is also repeated for the goals and obstacles, where the largest 3 areas are contoured. Once this has happened for all objects, the distance and center x-axis bearing for each is returned to the navigation code and distributed to the necessary subsystems, allowing Steve to function properly.
So Steve uses what's known as a state machine to decide what he's going to do. A state machine is a loop where different values set the current state of the robot. In Steve's case, these include states such as searching for the ball, traveling to the ball once it's been seen, checking behind obstacles, finding the goal, and kicking the ball. Then it all repeats. Once you have these states set up, you can start to add things like obstacle avoidance. Currently, Steve doesn't have any advanced obstacle avoidance, but the groundwork is there to implement it at a later date.
In the end, Steve was capable of finding the ball behind a signal obstacle with moderate accuracy and locating goals accurately. It struggled to capture the ball within the dribbler, but this was resolved with front pincers. While obstacle avoidance code was prepared, it was not tested before final demonstration, but it was perfectly fine in simulation. Even though he's not perfect, he can kick goals, and that's what really counts in football, and is why he's sponsored by Nike.